A 0.9 meters squared water pipe descends 10 meters and narrows to 0.25 square meters. The large end is at 1 atmosphere pressure. A. What is the water speed exiting the pipe? B. How long will the pipe take to fill up a 100,000 liter container? C. How long will the pipe take to output 100,000 kilograms of water? And finally, D. How long will the pipe take to output 100,000 newtons of water? I have a sketch over here showing V1 and A1 representing the pipe, the input. A1 is a large area, V1 is a relatively small speed. The pipe output is a larger V2 and a smaller A2. So we can write a Bernoulli for this pipe. And the pressure at the input and at the output are both atmospheric, so the P's cancel on both sides. If I take my potential energy reference to be the second pipe, level of the second pipe, then the H2 on the left side is 0. I can just set H1 equal to H. All other terms are proportional to rho, and so the rho's will cancel. And if I multiply by 2 through by 2, the equation I get is 2GH plus V1 squared is equal to V2 squared. This is a squared here. Okay, very good. So now we can use the continuity equation. The mass flow rate Q is equal to the input mass flow rate, volume flow rate, excuse me, A1 times V1, and that's going to be equal to the output volume flow rate, A2 V2. I'm interested in solving for V2, so I can solve this for V1. V1, the input velocity is A2 over A1 times V2. Now if I substitute that in here, I'll get 2GH plus A2 over A1 squared times V2 squared is equal to V2 squared. Subtract this from both sides and then divide, and I will conclude that V2 is equal to 2GH over 1 minus A2 over A1 squared, square root of that. So that's going to be equal to 2 times approximating G with 10 meters per second per second. The drop here is 10 meters. That's this drop from the output end to the input end, divided by 1 minus 0.25 meters squared over 0.9 meters squared. Square root of that. And that turns out to be 14.7 meters per second. That's A. Okay. Part B. How long will the pipe take to fill up a 100,000 liter container? Well, okay, 100,000 liters, 10 to the 5th liters. 1 liter is 1,000 cubic centimeters, so that's equal to 10 to the 8th cubic centimeters. There is 1,000,000 cubic centimeters in a cubic meter, and so if I multiply by 1 cubic meter divided by 10 to the 6th cubic centimeters, this converts to 100 cubic meters. And so to figure out how long it takes to fill this volume, let's figure out what Q is first. So Q, that's the volume flow, equal to A2 times V2. Since I've already solved for V2, it makes sense to use that one rather than A1 times V1. And that's going to be equal to 0.25 square meters times the velocity that we just calculated, 14.7 meters per second. And that gives me 3.7 roughly cubic meters per second. And so the time taken is going to be this volume divided by the volume flow rate, 3.7 meters squared per second. Note that I get time seconds if I do this, and that's essentially 100 divided by 3.7, which comes out to be 27.2 seconds. And that's how long it takes to fill up a container with 100,000 liters. Okay, part C. How long will the pipe take to output 100,000 kilograms? Okay, the insight there is that rho times Q has dimensions of kilograms per cubic meter. Those are the dimensions of rho. Dimensions of Q are cubic meters per second, and I get mass per unit time out of that, kilogram per second. And so I can convert the volume flow rate, Q, to mass flow rate simply by multiplying by rho. Okay, so my volume flow rate is 3.7 cubic meters per second. So let me identify a new variable here. M is equal to the mass flow rate, which is equal to rho times Q. And that's going to be 10 to the third kilograms per cubic meter. That's the density of water, times 3.7 cubic meters per second. So in other words, that's 3.7 times 10 to the third kilograms per second. And in order for the pipe to output 100,000 kilograms of water, 10 to the fifth kilograms, in other words, I simply take the 10 to the fifth kilograms and I divide by my mass flow rate, 3.7 times 10 to the third kilograms per second. And I get 27.2 seconds. Same thing I got for part B. Okay, for D, to get a Newton rate, I can simply take rho Q and multiply that by G. And so if I do that, let's call that W. That's going to be the Newton rate output of the pipe. It's going to be rho times Q times G. This gives me kilograms per second, and then multiplying by G gives me newtons per second. And so that's going to be basically, if I take G to be 10, that's going to come out to be 3.7 times 10 to the fourth, just adding a factor of 10 on here, in other words, and that's going to be newtons per second. And so now to output 100,000 newtons, the time is going to, required to do that is going to be 10 to the fifth newtons divided by 3.7 times 10 to the fourth newtons per second. And that's 10 divided by 3.7, so in other words it's going to be this divided by a factor of 10, 2.72 seconds.